Very good afternoon, students.
Good afternoon, sir.
Good afternoon.
So without wasting any time, let us start with the discussion. Last class, we have seen about different types of reactions, preparations, and all about alkanes. Now in today's session, we'll be looking at alkenes and its properties, preparations, and all. And after that, we'll look at alkynes and then benzene, right? That is how our process of study will go. So alkene, so whatever the hydrocarbon it is, whatever the function of just a second, I think there was a lag. I'll just refresh it once. Yes, students, is everything clear now?
Yes, sir.
Yes, right. So alkenes, we have to look at the methods of preparation as well as physical properties and chemical properties. So let us start with the methods of preparation. Any methods of preparation you know already, or from the GOC we have studied GOC, right? General organic chemistry. There we have seen different types of reactions: addition reactions, elimination reactions, substitution reactions. Any reactions can you remember or relate to where you can prepare alkenes as the final products? Or from the reactions whatever you have studied in the hydrocarbon, can we produce any alkenes? So if you think carefully, we can produce alkenes from alkynes by partial hydrogenation. If you do complete hydrogenation, the alkyne will be directly converted to alkane. But if you do partial hydrogenation, you will get alkene. From alcohols by dehydration. D means removal. Hydration means water. Dehydration, removal of water, you can produce again alkene. From alkyl halide, dehydrohalogenation. If you remember, from alkyl halides also we can produce respective alkenes, and there comes the discussion of elimination reactions. How many types of eliminations we have? Two types, E1 and E2. What is E2 elimination? E2 elimination will be done in the presence of strong base. What is the order of E2 elimination? Tertiary alkyl halide, then secondary, then primary. E2 elimination, how does the transition state looks like in E2 elimination? How does the transition state looks like in E2 elimination? It looks like alkene. Since the transition state looks like alkene, you have to always form the most stable alkene with some exceptions. Under what exceptions will form the least substituted alkene? When the base is bulky, when we have poor leaving group, or when we have extended conjugation. Can I say in the presence of poor leaving group, how the transition state looks like in E2 elimination?
Carbon anion.
Carbon anion, very good. In the presence of strong base and good leaving group, the transition states look like alkene. In the presence of poor leaving group, the transition state looks like carbon ion. You have to look at the stability of carbon ion and then only decide the major product and minor product. In E1 elimination, we will form carbocation as the intermediate. It's a two-step process. Since carbocation is there, rearrangements, ring expansions, ring contractions are all possible. That's what we have seen from the alkyl halides. And also dehalogenation of vicinal dihalide. From the vicinal dihalide, you can remove both the halogens if you treat with ZnBr2. Like if you treat with zinc, you will remove ZnBr2 or ZnCl2. So dehalogenation of vicinal dihalide will also form alkenes. Let us go with one by one. And how many types of partial hydrogenation you know? Lindless reaction, Lindless catalyst or Rosenmann's catalyst. And we have Betz reduction. In the Lindless catalyst, we'll get cis or trans?
Cis.
Cis. Very good. So from alkynes, we'll start with the reaction. RC triple bond Cr plus 2H2 in the presence of palladium, which converts the alkyne to respective alkane. the triple bond between two carbon atoms has been now converted to single bond. The two hydrogen atoms have been added from the same side. The hydrogenation in the presence of metal catalyst is a syn addition or an anti-addition?
Sin addition.
Syn addition. So the two hydrogens are going to be added from the same side. Why? Because the adsorption is going to happen only from when the hydrogens are added from the same side. So that is one point, students. This is complete hydrogenation will produce alkanes, but we require alkenes. Alkynes on reduction in the presence of pelletized charcoal, partially deactivated with poisons like quinoline, etc., gives alkenes. It is nothing but partial hydrogenation. We have seen one term known as poison here. Alkynes on reduction in the presence of pelletized charcoal, partially deactivated with poisons. What are poisons? Last class we have seen catalyst. What is the role of catalyst? Catalyst is substance which increases the rate of the reaction, which alters the rate of reaction, we can say. There are positive catalyst, negative catalyst also. So I can use a generalized term. Catalyst is something which can alter the rate of the reaction. Every catalyst will have some activity. The substance which increases the activity of the catalyst, what is that called as?
Promoters.
Promoter. The substance which can decrease the activity of the catalyst, what is that called as?
Poisons.
Poison. How the promoter can increase the activity of the catalyst? Last class I have explained you.
By increasing the distance between the
By increasing lattice spacing, you can say. How the poison can decrease the activity of the catalyst? Because that is also a question, right? It's not like poison means you have to remember. So these are actually decreasing the poisons can decrease the activity of the catalyst because they are acting as competitors. They will be acting as a competitors to the reactant molecules. The reactant molecules has to get absorbed, they have to react. Whatever the substance we say poison, that will also wants to go and get absorbed, that will also wants to react. Like if there are some 10 NEET colleges, every college has a capacity of 100 students, 100 into 10,000 students. 1000 students capacity is there for all the NEET colleges, let us say, and only 1000 students have applied. Then what is the cutoff? Whatever the least mark we get, that will be the cutoff automatically, because every student will be getting a seat. If 1000 students are there and 1 lakh students applied, what happens? We have to segregate, we have to select only 1000 from the 1 lakh. If 1000 seats are there and 10 lakh students applied, like if the competition gets increased, what happens? The chance of getting selected will decrease or not? Yes or no? I'm saying this as generalized case, not applicable to individual persons. Okay, think of generalized case. If the more number of people are going and absorbing on the same surface, then the reactant molecules getting reacted will decrease or not? Obviously, that will happen. The same thing, the poison will do the same thing. The poison will act as a competitor for the reactant molecules for the reaction to be done. So that poisons like a quinoline are there. And here we will be having the hydrogenation stopping at only alkene stage, not venting up to alkane stage. The partially deactivated pelletized charcoal is known as Lindlar's catalyst. If you use barium sulfate, what is the name changes? RC triple bond C plus H2 in the presence of palladium and charcoal in the presence of quinoline will give RCH double bond CH R, and you will get what type of alkene? Cis alkene. But if you take barium sulfate, the name is going to change to Rosenmann's catalyst or Rosenmann's catalyst or reaction. So RC triple bond C R plus H2 in the presence of palladium and charcoal and quinoline, it will stop the reaction at the alkene stage because quinoline is going to act as a poison. How it can act as a poison means it will be acting as a competitor to get absorbed on the surface where the reactant molecules are getting absorbed and they are reacted. If the competition is increased, the reactivity is obviously going to be decreased. So all the hydrogenation like alkyne to alkane stage is not going to happening directly where the hydrogenation stops at alkene stage. That is nothing but partial hydrogenation. Promoters increase the activity of the catalyst by increasing the lattice spacing. Poisons decrease the activity of the catalyst by acting as competitors. R C triple bond Cr plus H2, palladium in the presence of CaCO3. It is nothing but Lindlar's catalyst, or you can also take charcoal. It will form cis alkene, RCH double bond CHR. You can take palladium in the presence of BaSO4. It is nothing but Rosenman catalyst. Whenever you use barium sulfate, the name changes. Palladium in the presence of barium sulfate is Rosenman's catalyst. Here you get a RCH double bond CHR. Same cis alkene is going to be obtained. Same cis alkene will be obtained because the hydrogens which are going to be added to this carbon triple bond carbon, they are added from the same side. So you'll get cis alkene. Is that clear, students? Very simple.
Yes.
Yes,
Yes,
sir.
right. Very good. So in the case of Birch reaction, the next reaction is for partial hydrogenation. Birch catalyst like sodium in liquid ammonia is also used. Here adsorption is not the scenario where base tries to pick up the proton and all things happen. Birch reduction is RC triple bond Cr plus Na or lithium, sodium or lithium in the presence of liquid ammonia. They will form respect to NH2 minus, and from there the hydrogens are going to be added. So whatever the alkane you have, that is going to be converted to alkane only. But whatever the alkene is going to be formed, that is going to be trans alkene, not cis alkene, and the mechanism is not required. The trans alkene is obtained because the hydrogens, what are they are going to be added? They are added from the opposite sides, not from the same sides. Terminal alkynes do not give Betz reduction. Any reason can you think of? Terminal alkyne, like you can take RC triple bond CH. It is a terminal alkyne. If I treat with this sodium or liquid lithium in liquid ammonia, I am not saying this will be converting into respect to alkene. Why?
Hydrogen's lost.
Because terminal alkynes, they have acidic proton. Okay. Terminal alkynes, because of acidic proton, they will be undergoing acid-base reaction, forming respect to C minus Na plus. Okay. Terminal alkyne possess acidic proton, forming salts. That is undergoing acid-base reaction. Undergoing acid-base reaction. Right, students? Yeah, same example given. RC triple bond CH, sodium or lithium in the presence of liquid ammonia will form RC triple bond C minus Na plus half mole of H2 is obtained, because whatever the H plus ions which are lost, those H plus will take the electrons to form hydrogen atoms. The hydrogen atoms are not stable in the isolated stage, rather they combine with other hydrogen atoms to evolve H2 gas. Right? So Betz reduction means trans alkene is obtained, and the catalyst, Betz catalyst is sodium or lithium in the presence of liquid ammonia. Rosenman's catalyst or Lindlar's catalyst will form cis alkene because we are using the poisons, right? Because of the use of poisons, the reaction is stopped at only alkene stage. That is the first method of preparation of alkene, that is partial hydrogenation. The second method is from alcohols, that is by dehydration. Dehydration, as I have told you, removal of water from that respect to alcohol. Dehydration reaction proceeds through 3 steps are there in this particular reaction. What are 3 steps? Can anyone think of? Alcohols on heating with a concentrated H2S4 gives alkene with elimination of water molecule. This is known as acid catalyzed dehydration of alcohols. Acid catalyzed, they are saying acid is used as a catalyst because the H plus ions, whatever they are used in the initial step, they are released back. Then only we can say the acid is just actually catalyzing the reaction. If H plus ion is used up in the reaction, it is not a catalyst, it is a reagent. We have to take that in stoichiometric amount. What are the reagents? Concentrated H2S4 on heating, H3PO4 on heating, H plus on heating, or KHSO4 on heating. You may ask a question, sir, here KHSO4 means no H plus ion. How does this act? KHSO4 will give K plus and HSO4 minus. HSO4 minus can react with water to form to produce again H plus ion, that is H2S4 is obtained, which can release back the H plus ion. So what is the reaction mechanism? So we have CH3, C, CH3, CH3, OH, whatever the molecule they have given to you, let us start with this only. We are treating this with H2S4 upon heating. Heating has to be mentioned for sure. Why?
Because elimination will occur so that alkene will be formed.
Yeah, elimination will occur, alkene will be formed. Why heating is required? If heating is not mentioned, what you have to do? You can do substitution, because elimination requires breaking of bonds. It requires high temperature. Right? So we have respect to alcohol, H plus ion is obtained from H2S4. Let us write the reaction H2S4 giving respect to H plus and HSO4 minus ion. There's an establishment of equilibrium. So lone pair of electrons on oxygen picks up the proton, forming respect to protonated alcohol. Step 1 is simple. Lone pair of electrons present on oxygen attacking the H plus to form protonated alcohol. The OH is going to be converted to OH2 plus. Step 2, loss of water to form respect to carbocation. Loss of water to form respect to carbocation. First step is protonation of alcohol. Protonation of alcohol. Second step is loss of H2O to form water. To form loss of H2O to form carbocation. Carbocation. Once the carbocation is formed, rearrangements you can do, ring expansions you can do. That depends upon what type of carbocation is there. Here, is there any rearrangement possible? Further rearrangement?
No, sir.
No, sir.
Because it is already the most stable carbocation, no other rearrangement. So what happens now? HSO4 minus, which was present in the reaction mixture, H2SO4 is an acid. HSO4 minus will be respective conjugate base. HSO4 minus will try to pick up this proton. CH electron density comes into forming CH3, CH3 double bond CH2, which is nothing but your alkane. And the temperature, high temperature they have mentioned, especially it has to be around 170 degrees. Temperature has to be 170 degrees. So CH3, CH3 double bond CH2, alkene is going to be formed. So elimination to form alkene. Since alkene is going to be formed, the most substituted alkene is going to be formed as the major product. So this was the mechanistic approach. So protonation of alcohol, loss of water to form a carbocation, and elimination to form a respective alkene. Right, students? Now let us take different examples. One ring expansion example, simple example I'll give. So I'll give a 4-member ring, alcohol, and ring expansion. Is it a rate determining step or not?
No, sir.
No, sir.
I have told you many times. So this example you can do, all of you. Very simple example. So what happens in the first stage? The 4-member ring will be present. CH3 ring as it is. OH will be converted to OH2 plus. OH2 plus, and loss of water to form a respective carbocation. Methyl will be present here. You form a carbocation. Give numbering 1, 2, 3, 4, 5. 2, 3 bond or 2, 5 bond you can cleave. Simply connect the first and third carbon atoms. So which carbon has seen the net loss in electron density? 1, 2, 3. 1 is connected to 2, 2 to 5, 5 to 4, 4 to 3. First carbon gained the electron density, so positive charge nullified. First carbon has methyl substituent. Third carbon, no loss, no gain, so no charge developed. Second carbon, seen the net loss, so positive charge. It has a methyl group. Now HSO4 minus, whatever it is present, that will try to pick up the proton in such a way such that you will get the most substituted alkane. So this alkane will be your major product. I think every step is clear to you or not?
Yes, sir.
Yes, right? Right. Last class, I have given one example, if you remember. Last class,
Yes, sir.
I have given one example where that is a dehydration reaction. Anyone tried that example?
Yes, sir.
Yeah, what is the product, Faizan?
Sir, it will be like a benzene ring. That second one.
Second one is benzene ring. How come?
Sir, OH minus will be removed, then resonance will take place.
Yes, very good. That will be benzene ring. Okay.
Yes, sir.
So first step is H2SO4 trying to pick up the H2SO4 will release the H plus ion. Lone pair of electrons on oxygen will try to attack the H plus to form OH is now going to be converted to OH2 plus. Loss of water will occur to form respective carbocation. If you think of stability of this particular carbocation alone, so it is already 3-degree carbocation. You can think of two attacks like HSO4 minus picks up proton from here or from here. So if HSO4 minus picks up proton from here, you can generate this particular alkene. Or if HSO4 minus picks up proton from here, it can also form this particular alkene. So that becomes alene system or not? Alene system, anyone remember alene system? Alene system means how to decide whether plane of symmetry is possible or not. Like how to decide when optical activity is possible or not. Remember optical activity alene systems or not? Whenever we have even number of double bonds, the terminal carbon atoms should, if they contain different groups, there will not be any plane of symmetry. In that case, they are going to be optically active. If the even number of double bonds are there and the terminal carbons whose valences are perpendicular, if they have same type of groups, then obviously there will be a plane of symmetry, no optical activity will be present. So if this proton is picked up, then you are getting some alene system where this carbon has to be sp hybridized. But here, if you look at this particular shape, it was at an angle, but it was forced to come out of that angle because of that alene system. So these are the two possibilities which you can think of if you try to do the elimination from this. But you can also proceed with the resonating structures. Although it is tertiary carbocation, it is not just a treated as tertiary, it is an allylic system or not. So if you try to write the resonating structure, this carbon-carbon double bond moves away. Positive charge will be present here. And next carbon-carbon double bond moves away. Positive charge will be present here. We get double bond position here. Double bond positions are changed now. And ultimately, we can do 1,2 ethyl shift. If 1,2 ethyl shift can occur, we can generate even more stable carbocation, which is 3 degree. 1,2 ethyl shift. If 1,2 ethyl shift you can do, in that case you will be generating this particular carbocation. Now again you can think of HSO4 minus picking up the proton available here as well as here. HSO4 minus picking up this proton will generate this intermediate, this type of product, double bond here. HSO4 minus picking up the proton from this particular carbon generates a benzene ring. A benzene ring is obtained. This is nothing but your major product. Okay. So whenever you have the positive charge carbocation, if it is in resonance, you have to try to write the respective resonating structures and then decide wherever there is an aromatic stabilization gains, then obviously that is going to be the major product. You may ask a question, sir, how do you know that after these some 4-5 steps you will get this aromatic? You have to write the resonating structures. Sir, why the molecule will undergo these many steps? All these steps will not be taking much time. It will be happening in 10 power minus 8 to 10 power minus 9 seconds. Only rate determining step is the slowest step. Remaining step will happen at a greater rate. Are you understanding this or not? Since we are writing these many steps, in reality there are no such many those many steps present for longer times. It's all moving simultaneously. It's all happening simultaneously. Okay, students, is that clear?
Yes, sir.
Take this example as homework. Here I am specially mentioning 170 degrees Celsius. If the temperature is reduced to 140 degrees Celsius, what you are going to do? If I give a reaction in this manner, CH3, CH2OH treated with H2S4 in the presence of 140 degrees Celsius, what will happen now? First case, second case. First case you take as homework. Second case, can I discuss? Like 140 degrees Celsius is not sufficient to do elimination. In the presence of 140 degrees Celsius, what will happen is the CH3, CH2OH is there, right? That OH will be converted to respect to OH2 plus. First step is simple. Now in the second step, what happens is we have another molecule of CH3, CH2OH, right? This other molecule of alcohols are also going to act as nucleophiles. Alcohols can also behave as nucleophiles. Yes, Suman?
Sir, in the last question,
Which question?
that is a Bridget carbon. No? So the last question, not H2 sober and
Is that a bridged carbon? Like it's not like a bicyclic carbon, no. Like two rings are not like in this case you can think of bridge. Like this is a bridge. This is one ring. Okay, this is like a fused carbon only, not like a bridged carbon. You will be getting this particular ring, right? And you will be getting this particular ring. Okay, here you are not supposed to apply Bretzel and all. Here positive charge can be possible. Okay.
okay, sir.
So now we have taken alcohol CH3 CH2OH converted to CH3 CH2OH2 plus. The second molecule of alcohol will now act as a nucleophile. It tries to attack the electrophilic carbon because here the temperature is not high, no. So what happens is the next molecule of alcohol is now going to attack as a nucleophile. It tries to attack the electrophilic carbon, leading to the formation of ether. Here ether formation occurs. Ether formation occurs as temperature is 140 degrees Celsius. Okay. So this is your dehydration of respective alcohol reactions and different example. You take this first example as homework. Very simple. You get a positive charge here. You can do the ring expansion. 2 6-member rings will be fused, and there in between you get a double bond. You try it out. Just the same protonation of alcohol, then ring expansion, 6-member ring, generating more stable carbocation if it is not present by doing hydrate shift and all. Finally, doing elimination such that the most substituted alkene is obtained. You will get this type of alkene. Check out. Right, students, let us proceed further. From alkyl halide by dehydrohalogenation. Dehydrohalogenation of alkyl halide to form alkene is an example of alpha beta elimination reaction because hydrogen removes from beta carbon. So a lot of examples we have discussed. Alkyl halides RX on heating with alcoholic potash eliminate one molecule of halogen acid to form alkene. So we'll get alcoholic KOH. OH minus will try to pick up the proton. That proton is going to pick up. CH electron density comes into. CX will leave. So transition state looks like alkene. TS looks like alkene. Alkene like transition state. And is there a condition to form only cis alkene or trans alkene? Or both can be formed? One day we have discussed about some Fischer projections. If you remember, Fischer projections have converted into Newman projections. From there, I have done the elimination such that the leaving group and the hydrogen they have to be they have to be 180 degrees to each other. That means anti-elimination should occur. The elimination E2 elimination follows anti-path. That is, E2 elimination is anti in nature. It does not say that cis alkene is obtained or trans alkene obtained. Both can be obtained. Only the elimination is anti in direction. Understand this point carefully. Okay. So let us look at some examples, whatever we have discussed in that elimination reactions. Just a second. Yes, like if you take an alkyl halide with alcoholic OH, OH minus picks up this proton, the CH electron density comes into the CCl bond cleaves, and this transition state is looking like alkene, and immediately it will form to the more stable alkene. And we know tertiary alkyl halide will undergo E2 greater rate than secondary than primary because of more number of hyperconjugative structures in the stability of alkene. Base OH minus cannot pick up proton from the same carbon to which halogen is connected due to steric repulsions. Base OH minus will pick up proton from that beta carbon, which will produce most substrate alkene or sets of alkene, but there are some exceptions. Yes or no? E2 elimination is anti-elimination. If I take this particular alkyl halide, you will get this particular alkene. These are all the same things which you have discussed. Try to write the IUPAC name of this product. Why? Because the elimination has to happen from the other hydrogen, other carbon only, because these two, this hydrogen and this chlorine, they are on the same side. In case of bulky base, in case of poor leaving group, in case of extended conjugation, you have Hoffman's product. All these examples clear or not, students?
Yes, sir.
Yes, no. So the same examples we can be again discussing here as well. So that's what your preparation of respect to alkene from the alkyl halide. The more details again, the whatever the reactions I have explained, the same things we'll repeatedly study here as well as in alkyl halides. In alkyl halides also again it is repeated because that is a reaction of alkyl halide. Fourth one, dehalogenation of vicinal dihalide. Like vicinal dihalide, whatever you have, dihalides in which two halogen atoms are attached to two adjacent carbon atoms. If the two adjacent carbon atoms have two hydrogen atoms or two halogen atoms attached, then they are said to be vicinal dihalides. If to the same carbon atom two halogens attached means, then they are called as geminal dihalides. Yes or no? Vicinal dihalides on treatment with zinc metal eliminate a molecule of ZnX2 to form respect to alkene. This is nothing but a dehalogenation reaction. And zinc will be respectively oxidized to Zn plus 2 and 2 electrons are lost. And what was the driving force for this reaction? The same thing we study in the electrochemistry, if you remember galvanic cell. Zinc placed in ZnSO4, copper placed in CuSO4. Zinc will undergo oxidation to Zn plus 2, copper plus 2 ions from the solution they go and deposit on the rod to as copper. Why zinc will undergo oxidation to form Zn plus 2? Why not Zn plus 2 from the solution go and deposit as zinc metal? Why, students? Anyone?
Reduction potential.
Yeah, that's what why, Suman. Yeah, reduction potential only. Why? That is the question, no? Reduction potential means why the reduction potential is for zinc is like that. That depends upon radius ratios, okay? Because reduction potential values depends upon what ultimately? From the metal, if we say Zn plus 2 is coming out, what you can think of? Like this is a metal, imagine this remote whatever is present here is a metal. From the metal, I have to remove Zn plus 2 ions. In the metal, we have metal kernels. Metal kernel, I have told you one day. Like what if the electrons are lost out from the zinc, the Zn plus 2 ions presented different crystal lattice sites. All the metal kernels will have electrostatic force of attraction with all the free electrons. That is nothing but metallic bonding. There is metallic bonding present in every metal. I have to generate or I have to remove zinc metal as Zn plus 2 ion means what are the type of forces I am dealing with? I am dealing with enthalpy of atomization. I am dealing with the metallic bonding. And Zn is converting it to Zn plus 2 means I am dealing with ionization energy 1 plus ionization energy 2. Zn plus 2, whatever it is coming into a solution, that will be having hydration enthalpy. All these energies are there or not? So whenever you think of enthalpy of atomization, crystal lattice structure comes into picture, because enthalpy of atomization depends upon what? Depends upon crystal lattice structure. Crystal lattice structure depends upon what? Depends upon radius ratios. So radius ratio depends upon what? Depends upon size. So based on size only, the radius ratios vary, or the radius of that particular, based on that only the crystal lattice structure vary. Based on the different crystal lattice structures only, we can say the enthalpy of atomizations vary. Based on enthalpy of atomizations only, the reduction potentials are also going to be varying. Okay, based on that only we can say zinc has a more tendency to undergo Zn+2 reduction potentials directly give the idea why a particular metal is converting into respective ion. Why can't other metal convert? Reasons are everything. If you go with the root cause, it depends upon size because crystal lattice structure. So zinc has a greater tendency to undergo Zn+2 based on its crystal lattice structure, and we all know we have studied D and F block where you can see in that D and F block whatever the structures they are going to possess, they have some typical crystal lattice structures that is mentioned as X. Why? Because again they have D10 configuration. The Zn+2 will have D10 configuration. Whenever they have D10 configuration, they have poor metallic bonding or not. Metallic bonding depends upon number of unpaired d electrons. If the unpaired electrons are not there, obviously metallic bonding will be affected. So these are all interlinked. So that details are not required for you, but I am just explaining. So vicinal dihalides on treatment with zinc metal eliminate a molecule of ZnH2 because in ZnH2 we have zinc in the Zn+2 ion, and this reaction is nothing but a dehalogenation. Reagents use zinc dust upon heating. C connected to bromine, carbon, bromine, carbon, bromine, treated with zinc Br, treated with zinc dust. Zn-Br2 is going to be lost, and you will have the carbon-carbon double bond formation. So whenever you have vicinal dihalide treated with zinc dust, Zn-Br2 is going to be lost, and you will get a respective alkene form. Is that clear, students? Yes or no?
Yes, sir.
Yes, right. What happens here? Very simple. What is the IUPAC name of the product form?
Propene.
Propene.
Yes or no? CH3, because two bromines are lost, we get the double bond. CH3, CH double bond, CH2, which is nothing but your propene. So these are the preparations of your respective alkenes. What are the preparations? Partial hydrogenation, dehydration of alcohols to form respective alkene. Dehydration involves protonation of alcohol, high temperature 170 degrees Celsius required. After protonation, you will get elimination of water to form carbocation. Then the rearrangements or ring expansions are possible. Finally, generation of more substitute alkene. Then you have method like treated with vicinal dihalide treated with zinc dust to form respective alkene, and also you have elimination E1 and E2 elimination of alkyl halides to form respective alkenes by dehydrohalogenation reactions. Those are the methods of preparations of alkenes. Physical properties of alkene. Let us look at physical state. The first three members of alkenes are gases. Next to 14 members are liquids and higher ones are solids. Why? The first three members are gases. Next to 14 members are liquids and the higher ones are solids. Why?
Because as molecular mass increases, their attractive forces increase.
Very good. Because with increase in the molecular weight, the van der Waals force of attraction increases. If the van der Waals force of attraction increases, liquefaction will occur. And if the very high van der Waals force are there, then we can also have solids. Because molecular weight is directly proportional to van der Waals force of attraction. Van der Waals force of attraction. Ethene is colorless gas with a faint sweet smell, and all other alkenes are colorless and odorless. Okay, this is a property which you have to remember. Solubility, if you think of solubility, alkenes are insoluble in water because water is polar. Alkenes are non-polar. The polarity in alkenes can be developed in the presence of some other reagents, like they can also be having electromeric effect. Alkenes are insoluble in water but fairly soluble in non-polar solvents like benzene and petroleum ether because like dissolves in like. We always go with the philosophy like dissolves in like. Yes or no? Alkenes are non-polar, so they are going to be dissolving in the non-polar solvents. Boiling point, if you think of boiling point always directly proportional to molecular weight. Heavier the molecular weight, heavier will be the van der Waals force of attraction, heavier will be the boiling point. Alkenes show a regular increase in boiling point with increase in size. That is true because boiling point directly proportional to van der Waals force of attractions. Van der Waals forces, which is directly proportional to molecular weight. And we have cisalkene and transalkene. Among cisalkene and transalkene, if you want to compare dipole moment or boiling point, that depends upon what type of groups attached to that cisalkene and transalkene. If both the groups are same, in the case of transalkene, mu net is equals to 0. In the case of cisalkene, mu net not equal to 0. If one is electron donating and other is electron withdrawing groups, then transalkene will have greater net dipole moment when compared to cisalkene, right? Based on that only, we have to compare the respective boiling points. So chemical properties, alkenes will undergo electrophilic addition reactions, free radical addition reactions, and also free radical substitution reactions, and also oxidation reaction. Electrophilic addition reactions, we have discussed these reactions or not? Did you remember anyone? Do you remember any reactions, whatever we have discussed in electrophilic addition reactions of alkenes? Free radical additions, free radical substitution.
Markovnikov.
Yes, Markovnikov rule. Any other reactions, like what additions we have discussed? So let us go back to that slide where we have already discussed, so that you will get an idea. So addition reactions involved addition of reagent to the substrate, and these are classified into three types: electrophilic addition, nucleophilic addition, and free radical addition. Electrophilic addition reactions, alkenes generally undergo electrophilic addition due to the attack of pi electron density of alkene to the electrophile in the first step. First step is attack of pi electron density of alkene to the electrophile. That is why it is said to be electrophilic addition reaction. So addition of halogen acids, CH3, CH double bond, CH2, HCl, pi electron density attacked H plus. As soon as the attack occurs, we get a carbocation. So more stable carbocation has to be obtained. So 2 degree and 1 degree obtained. 2 degree is more stable. So based on that, the chloride ion, which is acting as a nucleophile now, that will attack the most stable carbocation. Generation of carbocation is the rate determining step. Rearrangement and ring expansion or compression is possible. Right? Addition of halogen acids. Addition of halogens in the presence of non-polar solvents. Addition of halogens in the presence of polar solvents. Addition of NOCl, Tilden's reagents. All these are the examples which we have discussed. If you remember, we have taken a 5-member ring treated with HI, generated a 6-member ring. Ring expansion is not the rate determining step. These are the first set of reactions which we have discussed. Here, although we get a 3 degree carbocation, we do the hydrate shift to generate more stable carbocation due to more number of hyperconjugative structures. Here we have done the ring compression or contraction. Addition of halogens to alkenes in non-polar solvent like CCl4 or CS2. What is the intermediate here? A cyclic halonium ion 3-member transition state is obtained. Whenever you do the reaction in the presence of H2O, what happens? Cl2 in the presence of H2O.
OH minus acts as a nucleophile.
OH minus acts as a nucleophile or H2O acts as a nucleophile? Same
H2O,
3-member
sorry.
Okay, 3-member cyclic halonium is formed. H2O acts as a nucleophile. Loss of H plus occurs again. Those are also called as halohydrins, HOX. And car, cisalkene, anti-addition give racemic mixtures. Examples: 1,4 addition occurs in the presence of conjugated dienes. Why? Because whatever the 3-member ring is formed, the ring cleavage will occur because of resonance, not the nucleophilic attack happening directly. So 1,4 addition will occurs in the presence of 1,4 addition occurs in the presence of conjugated dienes. So in the case of nucleophilic atom present in the long chain only, then what happens? Cyclization can occur. Yes or no? Like we have taken a long chain where we have OH group present on one of the carbon atom. Since oxygen has lone pair of electron, it can act as a nucleophile and attack the electrophilic center, and cyclization can also occur. Addition of H2 in the presence of water. So water acts as a nucleophile in the second step. First step, same cyclic halonium formed. I'm just showing all these slides because you will get an idea. All these are discussed. Whenever we are looking the slides in the alkenes, you have to get the idea and catch it up. Alkyne also we have taken treated with Cl2 in the presence of H2O. We can add a H2O like a Cl2 in the presence of H2O twice because we have a triple bond here. Addition of water to alkene, this will happen in the presence of dilute acid. If you have concentrated acid, then SO3H is also going to be added. And the loss of H plus is resulting in the last step indicates the acid released back after every molecule completes the reaction. So catalytic amount of acid is sufficient. Addition of Tilden's reagent NOCl, this also proceeds to 3-member transition states. Okay, students, all of you got the idea what type of reactions we have discussed earlier. Electrophilic
Yes, sir.
addition reactions. Free radical addition reaction, we have one specific reaction. What is that reaction? Can anyone list out? What, Faizan? What is the free radical addition reaction? Addition of HBr in the presence of peroxide is free radical addition or not?
Yes, sir.
Yes, sir.
Okay. Addition of HBr in the presence of peroxide is free radical addition. HF, HCl, they are stronger bonds, so they will not undergo. HI is a weaker bond, but the I dot, whatever it is going to be formed, that will combine with other I dot to form I2 molecules. Free radical substitution reaction, can you think of which type of alkenes undergo free radical substitution? What substitutions? Can I say allylic substitution, benzylic substitution occurs? NBS, NCS? Yes or no? So
Yes.
electrophilic addition reaction, free radical addition reaction, free radical substitution reaction are the same reaction which you have already discussed. So again, we are going to see them. Electrophilic addition reactions. General mechanism, when the electrophile does not have lone pair of electron like H plus. When the electrophile do not have lone pair of electron, what is the intermediate? When the electrophile do not have lone pair of electron, then in the reaction, what type of intermediate is obtained? Carbocation is obtained. When the electrophile possesses a lone pair of electron, what type of intermediate is obtained? Cyclic halonium ion is obtained. Like Cl2, Cl is an electrophile, Cl plus, but it possesses lone pair of electron. In that case, you get a 3-member ring. H plus is an electrophile, but it does not have a lone pair, so it will form carbocation. Okay, general mechanism, when electrophile does not have lone pair of electron, so pi electron density attacks the electrophile, forming carbocation. 2-degree carbocation is more stable. Okay, more stable. The more stable carbocation will now attacked by nucleophile, and you will have the respective final product. First step is the rate determining step of this reaction, that is formation of carbocation. Carbocation is intermediate is formed, so rearrangement may be possible. Rate of electrophilic addition reaction depends upon what? Nucleophilicity of the alkene or not. Because if alkene is more nucleophilic, the carbon-carbon pi electron density is attacking the electrophile. If that attack is high, then what you can say? Then the respective rate towards electrophilic addition is high. When we can say that a nucleophilic attack is high or nucleophilicity of alkene is high? When the carbon-carbon double bond carbons, if they are connected to more electron donating groups, in that case, the electron density of carbon-carbon double bond increases. If electron density increases, then we can say it is more nucleophilic. So based on nucleophilicity, we can say. Sir, this is a bit difficult if you say. You can think of other way. After the attack, after the pi electron density attacking the respective electrophile, you generate a carbocation. Compare the stability in carbocation. Okay, one thing is rate of electrophilic addition depends upon nucleophilicity of alkene. More electron density present in alkene, more will be the attack. The other way we can say is, if the electron density attacks and produces a carbocation, we will compare the stability of carbocation. Yes or no? So let us look at the examples, you will get clarity. Compare reactivity for the electrophilic addition reaction of following compounds? A, B, C. What is the order?
A highest.
A,
A
B,
highest.
C.
With respect to first point, I can say two methyls are there. Two methyls are electron donating. One methyl electron donating, no electron donating. More electron donating group, more is the electron density. So A greater than B greater than C. With respect to more nucleophilicity of the alkene, I have commented A greater than B greater than C. Now I will comment on the carbocation stabilities. Here I will get 3 degree carbocation, here I will get 2 degree, here I will get 1 degree. So based on carbocation also I can comment the same. Yes or no? So 2 electron donating groups in first compound, only 1 electron donating group in second, no electron donating group in third. So A greater than B greater than C is the right order. What about here? Compare reactivity order for electrophilic addition reactions of following compounds. This is electron donating group. This is also electron donating group. This is electron donating group. This is electron donating group. CH3 electron donating group, NO2 electron withdrawing group. C will be least because it is withdrawing the electron density. Among A and B, where we have 2 electron donating group, but in A we have OCH3, which is electron donating through mesomeric. In B, electron donating by inductive. So A greater than B greater than C or not?
Yes, sir.
Yes or no?
Yes, sir.
I can say in A, both are electron donating group. In B also both are electron donating group. But in A, difference is methyl group is electron donating by inductive effect, but OCH3 is electron donating by mesomeric effect. That is one way of saying A has more nucleophilicity in the C double bond C when compared to B. Other way, compare the carbocation stabilities. CH3C plus CH3 OCH3. In B, we have this carbocation CH3C, CH3 plus CH3. In C, we have CH3, C plus CH3 NO2. Can I say in B, we have tertiary butyl carbocation. In C, we have NO2 group present. NO2 has positive charge and nitrogen. Two positive charge atoms side by side. This is unstable. So C is unstable. Try to compare A and B. Tertiary butyl carbocation and this carbocation in the compound A. Which is more stable? If you
A
look at
would
the
be more
carbocation,
stable.
yeah, A should be more stable because lone pair of electrons and oxygen in resonance, the back bonding will occur. So we have CH3C, CH3, C double bond O. Oxygen has only one lone pair now and a positive charge and OCH3. But why you are saying A is more stable even though oxygen has positive charge?
Complete octet.
Complete octet on each atom. Okay, so that is why it is extremely stable. Octet complete. Complete octet in each atom. So that is why A will be more stable. So like that you can comment on which is more reactive towards electrophilic addition reactions. Compare here NO2 electron withdrawing group by mesomeric effect. Cl electron withdrawing group by inductive effect. CH3 electron donating group by what effect?
Hyperconjugation.
Hyperconjugation.
Hyperconjugation. OH is electron donating group by mesomeric. Which should be great?
Hyperconjugation.
No, what is the order? I mean
PCBA.
electron D will be greatest because it is electron donating group,
Yeah.
which will be stabilizing the respect to carbocation form or which will increase the electron density. So D, C, B, A, that will be the right order. NO2 is electron withdrawing group by mesomeric, so it withdraws the electron density greatly, so it destabilizes the system or it decreases the nucleophilicity of the respective compound. Okay, so D, C, B, A, that is the right order. Got it? Carbocation intermediate, carbocation rearrangements observed in those reactions in which carbocation is formed as an intermediate. Less stable carbocation rearranges itself to more stable carbocation via a transition stage. One carbocation to other carbocation, whatever the hydrate shift or methyl shift or phenyl shift you are doing, in between those shifts, there is a transition state always. Understand that point carefully. In between every step, there will be a transition state. CH3, CH2, CH2 plus, it will rearrange to form secondary carbocation. 1, 2 hydrate shift occurs. Yes or no? This is the respective transition stage. bond breaking, bond form. This bond is about to be formed, this bond is about to be broken. Transition state 1, 2, shift. What is shifting? Hydrate shift. So CH3, CH plus CH3. So this is the transition state in that particular rearrangement. Okay, because of the positive charge on this carbon, this CC electron density moves, developing delta positive on this particular carbon. Because of that, the CH bond slightly becomes weaker, and the new CH bond is about to be formed. Here transition state occurs. Here hydrate shift occurs. 1, 2 hydrate shift. 1, 2 hydrate shift, and you will be generating more stable carbocation. Yes or no? 3-degree carbocation is going to be formed. Here we will have the shifting possible or not possible, students? First case, what happens? 1, 2 hydrate shift. Then what happens? 1, 2 methyl shift. 1, 2 hydrate shift followed by 1, 2 methyl shift. So 2 times also you can shift. Okay. So 1, 2 hydrate shift if you do, you will be generating 2-degree carbocation. If you try to shift the methyl group again, you will generate the 3-degree carbocation. 1, 2 hydrate shift, 1, 2 methyl shift will produce the most stable carbocation. Here what type of shifting happens? 1, 2 hydrate shift, 3-degree carbocation is obtained. Here 1, 2 hydrate shift, again 1, 2 hydrate shift, we generate 3-degree. 1, 2 hydrate shift, again 1, 2 hydrate shift, you can generate 3-degree carbocation. Here in the sixth, what type of shifting occurs? What type of shifting occurs in the sixth compound? One, 2 hydrate shift or methyl shift? No one? Right or
Hydrate shift.
hydrate shift. Remember this point very carefully. The carbon bearing a positive charge, if it is unsaturated, no shifting possible. Rearrangements are not possible. If unsaturated carbon has positive charge like vinylic carbon or arylic carbon, that will never rearrange. Ring expansions are also possible. So if there is a carbon positive next to 4 or 5 member ring, then ring expansion takes place to generate more stable rings. These are all we have applied already. Okay, now we are just again learning. 4-member ring converts into 5-member ring, and 5-member ring converts into 6-member ring. But 6-member will never convert into 7-member because 6-member rings are more stable due to chair form, board form, twist board forms and all. Like if you have a carbocation like this, we'll generate what? 1, 2, 3, 4, 5. I'll just give the numbering. Although here numbering is not given, you give numbering. First is connected with fifth. 1 to 2, 2 to 3, 3 to 4. Which carbon will have positive charge? Second. Okay. You give numbering, students, because that will give clarity where the substituents are present and how are they present. 5-member ring, again you can give numbering. You can just form the 6-member ring. And one of the carbon atom of 6-member ring that will have a positive charge now. So 4-member ring to 5-member ring or 5-member ring to 6-member ring expansions are possible. Here expansion is possible or not possible? Give numbering 1, 2, 3, 4, 5, 6. 2, 6 I am connecting, 1, 6 you can have. On the first position itself you have 2 methyl groups. So you have 2-degree carbocation. The methyl shift can occur to produce 3-degree carbocation. So methyl shift can occur. So this is the most stable carbocation. So after doing ring expansion, you can again do the methyl shifting or ethyl shifting. Is everything clear, students, so far?
Yes, sir.
Right. Reaction with halogen acid. Which halogen acid will react greatly? HCl, HF, HBr, HI. Until now I have changed the alkene. Which alkene will react greatly towards electrophilic addition reaction? That alkene which has more nucleophilicity. Now I am changing the halogen acid. That halogen acid where the hydrogen halogen bond can be cleaved easily, that will react greatly. So HI will be undergoing the reaction at a greater rate. RCH double bond CH2 plus HBr. The pi electron density attacks, generating RCHBr CH2H. Hydrohalogenation. Pi electron density attacks H plus to form 2-degree carbocation. Br minus now attacks the carbon to form RCHBr CH3. RCHBr CH3. Carbocation intermediate is formed, so more stable carbocation you have to produce. Rate of reaction will be HI greater, then HBr, then HCl, then HF. HI greater, then HBr, then HCl, then HF. Because the reaction includes the bond cleavage of halogen acids. Right? Example, try to solve this. What is the IUPAC name of the product obtained? Within 5 seconds, you can answer this.
2-bromobutane.
Bromobutane.
2-bromobutane. Right? Very good. So lone pair of pi electron and attacks H plus, you will get CH3, CH2, CH plus, CH3. Br minus attacks the carbon. So you get CH3, CH2, CHBr, CH3. And can I say racemization occurs here? Because whatever the carbocation is formed, that is having trigonal planar shape. So nucleophilic attack can happen from the top as well as from the bottom. And also there was no group which is leaving group. There is no leaving group. So racemization can occur here. Markovnikov rule. The rule states that negative part of the reagent gets attached to that carbon of double bond which possesses lesser number of hydrogen atoms. Negative part of the reagent, that is X minus ion, will attach to that carbon which contains least number of hydrogens. RCH double bond CH2 treated with HBr. It forms RCHBr CH2H because this carbon has only one hydrogen. This carbon has two hydrogens. So one hydrogen and two hydrogen, if you think carefully, yes or no? One hydrogen is less, obviously, to this particular carbon. Halide ion is going to be attached. Markovnikov rule is not applicable if alkene is symmetrical because the halide ion can attack to any of the carbon atom, both are same only. Markovnikov rule is not applicable in the cases where double bond carbon is directly attached to strong electron withdrawing groups, these groups. Why? Because if you think of pi electron and attacking H plus and generating NO2 CH plus CH3, this NO2 already has positive charge, like a electron withdrawing group decreases the electron density on this particular carbon. Yes or no? So two positive charges present on the adjacent sides, like carbon bearing positive charge cannot be connected with NO2 which already has positive charge and nitrogen. So this will not be following. So here anti-Markovnikov rule will happen. Markovnikov rule is not applicable in the cases where double bond carbon is directly attached to strong electron withdrawing groups, like NH3 plus CH double bond CH2 HBr. Here also NH3 plus is connected to CH plus, like charges should be kept at maximum separation. Should be kept at maximum separation. Unlike charges at minimum separation, like charges at maximum separation, that will stabilize the respective intermediates. Is everything clear, students, so far?
Yes, sir.
Yes. If you remember, all these points are the same points which you have discussed. It's like a practice for your upcoming tests also. What will the major product here? IUPAC name within 5 seconds.
2-bromo-3-methyl-butane.
That's why you should not be confused. Again, try.
2-bromo-2-methyl-butane.
Okay. Don't get confused. Okay. You attacking the pi electron density, you get a positive charge here. Hydrates if you do positive charge here. Br minus attacks here. Got it? CH3, CH, CH double bond CH2, H plus, pi electron in statax, generates 2 degree carbocation. Now hydrate shift occurs, generates 3 degree carbocation, Br minus attacks. So 2 bromo, 2 methyl, butane. That will be the right answer. Here what happens? Pi electron in statax will generate CH3, C, CH3, CH3, C plus single bond CH3. Of course CH. Methyl shift 1, 2 methyl shift. CH3, C, CH3, positive charge, CH, CH3 and CH3, Br minus attacks. CH3, C, CH3, Br, CH, CH3, CH3. Okay, very simple questions. Same, we have to attack the pi electron to the H plus, form the respective carbocation, do rearrangements if possible, then do the nucleophilic attack. Where you will get the positive charge? Obviously, the positive charge will be obtained here because that will be stabilized by resonance. Br minus attacks here. Everyone got this or not, students? Because whatever
Yes,
the positive charge we have obtained here, that is actually stabilized by resonance. So because of that, this particular benzylic carbocation is obtained. Br minus attacks this particular carbon, generating this particular alkyl halide. Here ring expansion occurs. So we'll generate a pi electron and attacking H plus. Positive charge present 1, 2, 3, 4, 5, 6. 2, 3, 1, 2, 3 bond I'll give. I'll connect the 1, 3 now. First and third, first and second, second to 6, 6 to 5, 5 to 4, 4 to 3. First has methyl substitution, second has in the net loss. Now I'll do 1, 2 hydrate shift. I'll get the carbocation like this. Now Br minus or Cl minus, whatever is there in the reaction mixture. The halide ion acts as a nucleophile. Cl minus tries to attack as a nucleophile. Generate this particular compound as a major product. Right? Same. Ring expansion, then rearrangement, then nucleophilic attack. Reaction with dilute H2S4 or H plus in the presence of H2 or H2O plus. What is this reaction? Addition of water. Addition of water happens in the presence of some acidic medium, dilute acidic medium. If you have concentrated acidic medium, then what happens? Then SO3H will be directly added. And why do we require acidic medium?
Increase the nucleosity of alkyne.
Okay. If I take alkyne, is acidic medium sufficient? Yeah, that is true. Acidic medium is actually trying to increase the pi electron density attacking H plus so that the electrophilicity, the carbocation can be obtained easily. But if I take alkyne, we'll discuss that in alkynes as well. Just think on it. If I take alkyne, is acidic medium alone sufficient, or we need to use the mercury 2 salts? If I take C triple bond CH in the presence of H2O, H2SO4, we also need some HgSO4. So it will form respect to R C double bond CH2 plus. Now you will get RCOH double bond CH2, which can be tautomerized to form RC double bond of CH3. What is the role of H2S4? To increase the attack of the pi electron density to your respective H plus ion. What is the role of HgSO4 now in the alkyne? Why can't you take concentrated acid and do the reaction? Why can't you take concentrated acid and do the reaction? Why we require HgSO4? In alkynes, HgSO4 is taken to catalyze the reaction because the vinylic carbocation which is obtained, that is not stable. Okay, Hg2 is used as a catalyst. As a catalyst. Understand? So alkenes will be reacting, or addition of water to alkenes occurs in the presence of acidic medium. Addition of water to alkanes occurs in the presence of mercuric two salts. If they have not mentioned anything, simply alkane and Hg2C, you have to simply add water. Hg2, wherever you see, you have to simply add water. You may ask a question, sir, there is no water. No, water is a universal solvent. It is assumed to be there. Okay. RCH double bond CH2 plus H2O H plus, pi electron in state acts H plus, pi electron in state acts H plus, that is the first step. As soon as the pi electron in state acts H plus, we generate a carbocation. That carbocation, whatever it is formed, that is attacked by the nucleophile. What is the nucleophile now, students? Water acts as a nucleophile, attacks the carbocation, will generate the protonated alcohol, whatever it is there, right? That OH bond is going to be cleaved, loss of H plus occurs, ultimately you generate alcohols. So acidic hydration occurs, addition of water happened. Whenever you try to treat alkane with a H2O in the presence of H plus medium, addition of water occurs and carbocation is the intermediate. The same addition of H2O you can do with two other reactions which I have discussed earlier. What are those reactions? Addition of water to alkene. Anyone remember? Hydroboration, oxidation, oxymercuration, demercuration. Addition of
Yes,
water
sir.
to alkene occurs in the acidic medium, and rearrangements are possible because carbocation is the intermediate. Addition of water to alkenes occurs according to Markovnikov rule in oxymercuration, demercuration, and rearrangements are possible or not possible? Oxymercuration, demercuration, rearrangements possible, not possible?
No,
Not
sir.
possible.
Not possible. And if I take like whatever the water added, the OH groups forms from, in the oxymercuration, demercuration, OH comes from H2O, whereas hydrogen comes from NaBH4. If you take NaBD4, you will have deuterium added. If you take D2O, you have to add OD. Similarly, if you do hydroboration oxidation, it proceeds through what type of transition states? Hydroboration oxidation proceeds through 4-membered cyclic transition states. Oxymercuration, demercuration proceeds through 3-membered cyclic transition states. Hydroboration oxidation, anti-Markovnikov rule you have to do. Hydrogen is obtained from BH3 or B2H6. OH is obtained from H2O2 in the presence of OH minus and H2O. If you take B2D6, then you have to add deuterium. And no rearrangements are possible because carbocation is not the intermediate. Okay. So this reaction is reversible. Forward reaction is acidic hydration of alkene and backward reaction is acidic dehydration of alcohol or elimination reaction. CH3, CH, CH3, CH double bond CH2, H plus in the presence of H2O. What type of compound is obtained? I give you the IUPAC name of it.
2-methyl butane. Oh, 2-methyl butanol.
2-methyl butanol, is that
2
name
butanol.
correct name? 2-butanol, yes. Because you have to give the positioning of OH as well, right? The pi electron is stack H plus, we form a carbocation. The hydrate shift is going to happen, generate a more stable carbocation. Now H2 acts as a nucleophile, attacks. You get OH2 plus, loss of water, loss of H plus occurs to get respect to alcohol. So 1, 2, 3, 4. On the second position you have methyl, 2-methyl butan 2-ol. 2-methyl butan 2-ol. Okay. What happens here? What's the IUPAC name? Can I say 1-methyl cyclohexanol? Is that true or wrong?
Cyclopentanol, sir.
Yes, because ring expansion you should not think of because the positive charge is present in the ring. The pi electron instead attacks H plus, you get this type of carbocation. Yes or no? And H2O attacks, you get methyl and OH. So you have no ring expansion here. Okay, you should not think of ring expansion because positive charge is present on the 5-membered carbon only. Okay, so it is going to be 1-methyl cyclopentanol, not hexanol. Reaction with the constant H2SO4, students. Dilute H2SO4 means you have to add water. Concentrated H2SO4 means what you have to do? RCH double bond CH2 H2SO4 will form RCH HSO4, that is OSO3H is added and CH3 is as it is. Alkyl hydrogen sulfate is formed. Cold concentrated sulfuric acid adds to alkenes in accordance with the Markovnikov rule to form alkyl hydrogen sulfate by the electrophilic addition reaction. What happens? CH double bond CH2 treated with H plus from H2SO4. H2SO4 produced what? H plus ion and HSO4 minus will have this structure S double bond O, S double bond O, OH and O minus. The pi electron instead acts H plus will form RCH plus CH3. Now S double bond O, S double bond O, OH, O minus. This O minus attacks this particular carbon. RCH, O, S double bond O, S double bond O, OH and CH3. This is nothing but alkyl hydrogen sulfate. Electrophilic addition reactions. General mechanism, when electrophile has lone pair. When electrophile has lone pair means like Cl plus. In this case, what is the intermediate form?
Cyclic halonium.
Cyclic halonium, as we have seen a lot of examples. CH3, CH double bond CH2 plus electrophile. Pi electron density attacks the electrophile. Since a lone pair is present, lone pair also attack this particular carbocation, forming the, this is a RDS, rate determining step. So cyclic halonium is formed. The nucleophile will now attack the cyclic halonium ion in such a way such that the carbon electrophile bond is going to be cleaved. And you have to think carefully here, students. One thing is, you can think of nucleophile attacking the carbon where steric repulsions are minimum. Nucleophile attacking the carbon where it is behaving as electrophilic. Like think of steric repulsions now, steric repulsions. This is first one, this is second one. Which attack you should choose if you think of steric repulsions?
First one.
First one you have to choose. But what is actually happening here? Nucleophile is connected with the second carbon. So why nucleophile is connected to second carbon? Because the carbon electrophile bond, if that is cleaved, this carbon is getting more positive charge. So this carbon is behaving as more electrophilic in nature. This carbon is behaving as more carbocatenic in nature. Although carbocation is not the intermediate, based on more stable carbocation only we are attacking the nucleophile. Understand this carefully. Carbocation is not the intermediate, but positive charge developed on this carbon is more stabilized. So nucleophile is going to be attacking this particular carbon. This carbon electrophile bond is cleaved. First step is RDS, rate determining step. Carbocation intermediate does not form. Understand this point carefully. Carbocation intermediate is not formed, but the nucleophile attacks the carbon where positive charge is more stabilized. Okay. Carbocation intermediate does not form, so rearrangement is not possible. Reaction with X2 in the presence of CCl4. CH3, CH double bond CH2 plus Br2. What happens? Two bromines are going to be present, and the two bromines are going to be present in opposite side or same side?
Same side.
Same side or opposite side?
Sir, opposite side.
Anti-addition takes.
Anti-addition takes place, right? Very good. So first you get a 3-membered ring in this fashion means the Br minus whatever is lost that will attack from the opposite side, so that the two bromines will have minimum repulsions. Although they have mentioned in this side, you don't confuse because this carbon is a sp3 hybridized carbon. So whatever the bromine written here, that is not exactly present on the plane of the paper or plane of the screen. It will be in space. So CH3, CH double bond CH2 plus Br2 in the presence of CCl4. CCl4 is important, non-polar solvent. If you have polar solvent, that solvent water itself acts as a nucleophile. cyclic bromonium ion is obtained. The cyclic bromonium ion attacked by Br minus. Br minus attacks from the back sides, and this carbon bromine bond cleaves, generating vicinal dihalide. Vicinal dihalide is obtained. Right. Can I proceed further, students? Is everything clear so far?
Yes, sir.
Yes, sir.
Yes.
Right, very good. Electrophile contains lone pair, that is obviously noted. No carboxylic intermediate is formed, so no rearrangement possible. Reaction intermediate is cyclic halonium ion, as we have seen 3-membered cyclic transition states. Reactivity of halogens, fluorine is highly reactive, then chlorine, then bromine, then iodine. Reaction with fluorine is explosive. That's why we generally discuss chlorination and bromination. Iodination is very slow. Reaction with F2 is explosive. Reaction with I2 is reversible, because whatever the vicinal diiodide form, that will again react back to form respect to I2 and alkene. So it is reversible. Test of unsaturation, will it act as a test of unsaturation, this reaction? Because the bromine water decolonizes or not. Unknown organic compound Br2 in the presence of CCl4, reddish brown color disappears. The bromine water, whatever the color they possess, as soon as they react with the unknown organic compound, if the color is lost, that means that unknown organic compound should have the unsaturation. That means this is actually a tester to detect unsaturation present in the compound or not. Unknown organic compound treated with bromine in the presence of CCl4, reddish brown color disappear means unsaturation may be present. Alkane I have taken. I have added bromine water which is reddish brown colored water. I am adding to 3 cases, alkane, and alkane as well. If I look at alkane, even though I shake, that color is not decolorized. Whereas alkene and alkyne, the color decolorized. That means alkene and alkyne, the two compounds where the color has been decolorized, you can think of them as unsaturated compounds. Unsaturated compounds. Reaction with X2 in the presence of H2O. Now first step is same, formation of cyclic halonium ion. In the second step, earlier the halide ion act as a nucleophile, but now the water will act as a nucleophile. Water, as soon as it attacks as a nucleophile, it forms a positive charge on oxygen and 2 OH bonds are there. So the chloride ion which is left out in the first step, that will try to pick up the proton. So HCl is also obtained as a side product. CH3 CH double bond CH2 plus Br2, CH3 CHOH CH2Br, halohydrines are formed. So mechanism simple. The pi electron density attack the bromine to form cyclic halonium ion, which is nothing but your rate determining step. Now what is going to happen is, the lone pair of electrons present on oxygen, they are going to attack this particular carbon. Understand, nucleophilic attack is happening in such a way such that the carbon is the more positive charge on the carbon is more stabilized. So that carbon is getting attacked by nucleophile, not based on steric repulsions. So we get, actually we should get this compound CH3CH, lone pair of electrons on oxygen attacked. So 2 OH bonds should be present, only one lone pair and a positive charge, and CH2Br. Now whatever the Br minus which is left in the first step, that will try to pick up the proton. OH electron density is given to oxygen, generating CH3CHOH, 2 lone pair of electrons on oxygen, and the CH2Br. Again anti-addition is there, so OH and Br, they are opposite to each other. Right, same steps whatever we have discussed earlier. No carboxylated intermediate is formed, so no rearrangement possible. Reaction intermediate is cyclic halonium ion. Try to solve some examples. pH CH double bond CH2 in the presence of Cl2 H2O or HOCl. It will form pH CHOH CH2Cl. Yes or no?
Yes.
because first you will get a 3-membered ring with Cl plus, nucleophilic attack, H2O will be lost, H2O will be attacking as nucleophile, so OH will be present, loss of H plus occurs. So this is a cyclic halonium ion, so PH, CHOH, CH2Cl is going to be formed as the major product. Very simple question. Reaction with NOCl, Tilden's reagent, what happens? Here also 3-membered ring is going to be formed or not? Because here also electrophile possesses a lone pair of electron. Whatever the electrophile which possesses a lone pair of electron, that will form 3-membered cyclic transition state. So NOCl, nitrogen also has lone pair of electron, so it will form this type of intermediate. Mechanism will be CH3, CH double bond CH2 treated with NOCl. Pi electron in attacks carbon chlorine, nitrogen chlorine bond leaves. We get CH3, CH, CH2, NO. Now Cl minus acts as a nucleophile, attacks the electrophilic carbon, carbon nitrogen bond cleaves. CH3, CHCl, CH2, NO is formed. This reaction also we have discussed, Tilden's reagent also. Is that clear, students, so far?
Yes.
Yes, sir.
Yes,
Yes.
right. Very good. What happens in the first case? Because we have an alkene, it is not a Br2 addition in the presence of CCl4, no carboxylic intermediate, no ring expansion, nothing. 3-membered ring is going to be formed. The bromide ion will be attacking from the back side, forming vicinal dihalide. HOBr means Br2 in the presence of water. First is 3-membered ring, then attack of water, OH will be present here, bromine will be present on the other side. NOCl, so you have 3-membered ring like this, and NO is the intermediate. Cl minus will be present here because this particular carbon bearing positive charge is more stable, and NO will be present on terminal carbon. NO will be present on the terminal carbon. Same examples, same type. Oxymercuration, demercuration, and hydroboration oxidation. Reagent, mercuric acetate in the presence of water, that is first set. Oxymercuration, demercuration, NaBH4 in the presence of OH minus. RCH double bond CH2 treated with HgOAc taken twice H2O, followed by NaBH4 OH minus. Marconic of addition of water, OH and H are added. No rearrangements possible. 3-membered cyclic transition state is going to be obtained as the intermediate. Mechanism will be looking like this. I think we have discussed the mechanism or not previously.
Yes, sir.
Yes, sir.
Just let us look at this. We have discussed the mechanism also, right? Pi electron is attacking mercury, forming 3-membered ring structure. Then water acts as a nucleophile, attacks the electrophilic carbon. Then finally NaBH4 will be coming in and providing the hydrogen. Loss of mercury happens. Same thing we'll be discussing now. CH3 C double bond O Hg plus. So that will be attacking, forming a 3-membered ring structure. RCH HgOAc CH2 3-membered ring. H2 acts as a nucleophile. Lone pair of electrons on oxygen attacks. So you get OH, RCH OH CH2 HgOAc. This is treated with NaBH4 OH minus. Demercuration happens. So hydride ion will be attacking this particular carbon. Hg and OAc minus is lost, along with loss of Hg and OAc minus. This was the mechanistic approach. You don't need to go with the mechanism and all. Just to understand what the main points. Okay, no rearrangements. Water is giving the OH, NaBH4 is giving the hydrogen. So if you take D2O, you will get OD. If you take NaBD4, you will get deuterium. And Marconic rule is going to be happening and no rearrangements are possible. Is that clear, students? Everything so far?
Yes, sir.
Yes, sir.
Yes. So what happens? OH and H are going to be added according to Marconic rule. In this reaction, addition of water takes place and alcohol is formed as a product. No carbocation intermediate is formed, so no rearrangement takes place. Markovnikov addition of water. All the points are same, whatever we are going to discuss. What will happen here? D2O they have given. So we'll have to write CH3, CHOD, CH2H. That's it. CH3, CHOD, CH2H. Okay. Next class, we'll discuss about hydroboration, oxidation, and other reactions. Try to solve this particular question as well. So CH3, CH3. To this particular carbon, H2O is taken, OH is added. To the other terminal carbon, NaBD4 is taken, so deuterium is added. CH3, C, OH, CH3, CH2, D. It is going to be the respective major product. Okay, you don't need to write the mechanism always. You just simply try to attach. If H2O is there, you have to attach OH. If NaBD4 is there, you have to attach deuterium. Right, students? We'll discuss hydroboration, oxidation. Although we have discussed, we'll again see and then go with the next set of reactions. Fine. Thank you all, everyone. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.